Let's go into a little more detail on the filter specifications. So the first part of our specifications are the passband specifications, and these set a specific point which the magnitude response curve must go through. So for example, here we have minus 3 dB at 1 kilohertz, and you can see how our filter response curve goes through that point. Incidentally, this point is always going to be the lower right-hand portion of our passband region box. And you can see as we change this point, our curve will still go through that point. Now you might think that we would have the same thing happen with our stop band point. We would have this stop band and you would have the curve go through that stop band. And that would be the case if we could set a non-integer order filter. However, we're limited to integer order filters. So for example, a third order or a fourth order filter, not a 3.217 order filter. And because we're limited to integers, the filter response kind of jumps as it goes from third order to fourth order and so forth. And so we can't fine tune. So the best we can do is pick an order, pick the lowest order where the graph goes underneath that point that we specify. So in fact, the filter is a little bit better than what we specify. And finally, we have our filter response curve. And as we change that curve, it changes the shape, but it doesn't change the fact that we still go through that passband point and we still go underneath that stop band point. So what do we do with this information? Well, we take all this information and we pass it through a whole bunch of math, which you can find in a filter textbook, and we turn it into stage information. So we decompose the filter into these multiple stages, and each stage has three characteristics. It has a gain, it has a filter cutoff, which we specify as FP for pole frequency, and it has a Q, which represents the peaking. And so these are really the fundamental specifications that we're going to use to create the circuit in the next screen.